if someone wants to make sure that I do that again before when we break, that would be awesome too, because I sometimes forget about that. But all right. So I want to go through and quick, just to recap, because it's been a while since we've been out, talked about going through and looking at our assumptions of regression. We're going to start looking at some additional things. We got our accuracy, plausibility, missing values, univariate stuff, univariate outliers, linearity, homoscedasticity types of things. Okay. Remember that because we violate the fixed effects assumption of a regression, we now have to make sure that our data are multivariate normal in order for everything to work, right? So this is something that we want to keep an eye on in terms of our univariate and bivariate screenings with this stuff, right? But then what we're going to do is we're going to start to get into our residual assumptions. And residual assumptions, remember, we're wanting to see that our residuals are normal and independently identically distributed. Here, this first panel is what we would hope our residuals will look like. Your residuals will never look like this, given the nature of our data. There's always going to be weird edges and stuff like that going on. Our goal is to, or our job is to go through and say, is this something that's going to compromise my analyses, and then what types of things should I kind of be aware of, right? So we want to see normally and independently and identically distributed residuals. We want to keep an eye out for residuals that are non-normal, okay? Your residual, the mean of your residuals will always be 0, but we'll sometimes see things starting to skate down like this, right? So we want to take a look at normality of our residuals, both on the conditional distribution and the marginal distributions. We want to look for linearity stuff, right? Weird stuff like this where we see obvious non-linearities in our plots, and then heteroscedastic residuals. Again, what we're looking for are things where the widest spread is about 3 times the spread of the narrowest spot on our residuals, okay? So here we went through and took a look with some sample data at our residual plot. And we saw there's this weird kind of edge coming along this top that's kind of strange. But if you go through and you look at your univariate distributions, you'll see that for several of these variables, you kind of have a peak. I'm guessing this is probably because our measure of social support, which is our outcome variable, most people are kind of capping that out, peaking that out at the top, which is good because they're reporting high levels of social support. But it creates kind of this edge that we see running across here. Now, if we look at this, I'm not terribly concerned about the residual, even though I have some of this stuff. It looks like maybe down here we could have, for a couple of these values, something that looks like spots where there are negative skew, but overall, taking the whole thing into account, it's not beautiful and a nice, awesome cloud, but probably not something that we're going to get too worked up about. Something in the screening we would want to note, but not something that's going to sort of make us hit the brakes with things. Okay, just the same plot here in Stata. So this is, remember, what we're looking at is sort of normally and independently independently distributed residuals sort of going through there. Okay. Also, another thing we're going to do is look at normality of our residuals as a whole. Okay, this is our marginal plot. So overall, when we take a look at our residuals, are those plots looking normal? Okay, we're going to look at histograms, and then we have some probability plots, a little bit different. What this is going to do is this is going to plot things on diagonals generally, right? And this is just a nice way of visually of identifying deviations from normality. So we all can interpret a histogram and understand what that's looking like. But our probability plots, if our distribution is normal, we'll just see things on a straight line. If they're not, we start to get sort of curvilinear types of distributions. So for our data, we went through, took a look at our distribution here. It looks like we have maybe a few cases out here that are identified as low or low values for our residuals. This looks like we're missing some stuff here. But on the whole, nothing too bad in terms of normality. We see some deviations in our probability plot, right? Where we kind of drift off of this line, but not anything that would be consistent with something that we're going to be super concerned with. Okay. Questions up to this point? All right. Same thing in Stata. All right. And this is where we start getting into individual cases. Okay. We're wanting to go through and take a look at 3 different statistical constructs here. Discrepancy, we're going to assess this with our residuals. Discrepancies are weirdnesses going on in Y space. And we're going to look at these back. We're going to go back to our residuals to look at this. You'll see here in panel A, we've got a pretty large discrepancy because we've got a pretty large residual. Here's our observed value. Here's what we expected relative to everything else. We've got a pretty big discrepancy. So we would identify that as a potentially large residual. Okay. Here in the second plot, we've got something that's not a large residual, but it probably should be. Okay. If we remove this case, we've got this line going straight through these points with a perfect relationship. With this case out here, with the case in, it's a low discrepancy. It's a low residual. But if we take this case and look at where it is relative to the line that it would have been estimated if it had not been in there, we would see that that would result in a pretty large discrepancy. This is where our deleted residuals are going to come in. What we see is in this case right here, we would identify this. We're saying that this case is masking a problem, right? With it in there, if I'm just looking at my residuals, it doesn't look like it's a problem case at all. But if I look at everything in general, it's very clearly problematic in that it's dragging that whole regression line down, right? So this is why we go through. This is the exact case for why we are going to go through and primarily focus on deleted residuals, because a standard residual, that's not going to look like a problem at all or look weird at all. Studentized residual or studentized deleted residual is going to catch that. Okay. We're going to look at discrepancies, which we're going to assess through residuals. Leverages, these are multivariate outliers. Discrepancies are problems in Y space. Leverages are problems in X space. This is where we're going to start to catch weird combinations of variables or variables that deviate in Y space. Okay. Here in panel A, we don't have a problem with an unusual leverage because even though this dot is hanging out down away, it's a decent residual. In X space, it kind of lines up exactly where those other cases are. So it's not weird in X space. Here, what we have is something that if we look at this line, the actual estimated line, we have a small discrepancy, but we've got something that's a high leverage or a large leverage value because we've got a case that's really far out in X space. Everybody else is hanging out down here. We've got one case down here. So our leverage values are going to catch things that are univariate outliers, and that cases that are really large on maybe some specific predictor, but it's also going to catch, they're also going to catch things that are a weird combination of predictors. Okay. So we see that here. Here, again, a really large leverage case because the case is way out. Discrepancy is low, right? But here we've got a large influence point. Yeah.
Last one, I have written down on leverages that they're multivariate outliers.
It gets both of them.
Okay.
Yep. Yep. Again, you're looking at something, and you can see here in this one predictor case, it's that this is going to register. Both of these are going to register as high leverages, just because they're way out there. And this is what, as you're going through and running your screenings, you're going to want to keep a notepad and take note of those cases that are really high out there. This is why, since the beginning of we've been doing all this, I've had you making sure to write down the actual case numbers of weird cases, because what's going to happen is these cases are going to come up again and again and again. And the more times things come up, the more evidence that you have that maybe we let go of this person if there's something weird going on. Okay.
Yeah. If leverages also handle like univariate outliers, then I'm a little confused on what the difference is between like the discrepancies of the leverages.
Okay. discrepancy is, so here, your discrepancy is nothing because it perfectly falls on the prediction line, right? But it's a large leverage because it's way out there in X space. Thing about discrepancies is things happening in Y space, leverages happening in X space, either singly with a predictor or combinations of predictors, okay? Because then we get into influence. Influence is the extent to which the exclusion of a case is going to impact your model, okay? You think about your influence as the combination of discrepancy and leverage. We can have large discrepancies that don't impact our model all that much at all. We can have large leverages that don't impact our case much at all. But when we have something that has a high influence value, this is generally a combination of a high discrepancy and a high leverage, then we have cases that start to impact our model, our estimates, our coefficients, things along these lines, okay? So here, this is probably the best example of a high influence case, okay? We've got a case out here that I'm not going to catch if I'm just running my standard residuals because it looks pretty close. But if I look at my deleted residual, I'm going to see that I've got a problem here. I've got a problem in terms of my leverage because it's way outside X space. And all of a sudden, the inclusion or exclusion at this point changes my model dramatically in terms of that slope. These are the types of influence points that we're really kind of looking for. This is problematic. This is going to make these types of points are going to make your regression look a lot better than it is, because here we can kind of have maybe a cloud of points and then you got a couple of points hanging out there in the upper corner. It's going to drag that regression line out for something that would be sort of moderate and sort of break it up to here. These are the types of things we're really wanting to go through and take a look at, okay? And so there are different types of indices that we're going to look for this stuff, okay? So for our discrepancies, we're looking at this through our standardized residuals. Lots of different options for our residuals. We're going to look at deleted residuals for the reasons I just described, okay? Remember that our deleted individuals or our deleted residuals are going to look at the difference between some observed value of Y for our case X, whatever it is, and the expected value of Y in a model that excludes that case, right? So if we pull this case out, run the regression, find the regression line, and then look at where that case is relative to where the line would expect it to be if it had been included in that model, that's what's getting calculated in that deleted residual, okay? And the situation is, again, this right here. If I just look at my standardized residual, this is almost a perfect prediction, right? But if I pull this out, rerun the regression, and look where this case is relative to where the line would have been, now I've got a huge discrepancy going on there. And those are the types of things that we're wanting to do. So this deleted studentized residual or externally studentized residuals, these are going to go through and capture, making sure that we're not getting weird masking or swamping effects and things like that, okay? So again, the nice thing about these studentized residuals is they follow a t-distribution. So if I really wanted to put a p-value on any of those specific values, I could do it. The degrees of freedom are just the sample size minus the number of predictors minus 2. And I could just go through and attach a p-value to that. We're not going to do that because who cares about the p-value? All the p-value does is say that the residual is not 0. And I could probably look at the residual to tell whether or not it's 0. So, but what we're going to look at is absolute magnitude. Recommendations range from values plus or minus 2 to plus or minus 4. It really kind of depends on the situation. You know, if I have larger samples, I'm probably going to get some cases that I miss by quite a bit on. So I'm not going to get panicked too much. I'm just looking at things that are generally around those same values that we're looking at with univariate outliers and things like that. It's just a standardized score. We're kind of gauging sort of relative size of these. Okay, so if I go through and I calculate studentized residuals in SPSS, here's what I get for this model. And we already kind of looked at this a little bit, but any concerns with our residuals here? Anything here that looks like a problematic discrepancy? What do you think, Elizabeth?
Would it potentially be like a case that's 291 small?
One more time.
Is case 291 at the very bottom, is that problematic? Because it's that threshold of like negative.
Yeah, I mean, I might, and again, use that threshold very liberally. Like there's nothing, but yes, that is a case. And if I look at my box plot, 291 is way down here. I've got kind of a group of folks down here, but 291 is small. If I look at my histogram, I've got some stuff that's set away from the rest of the distribution. Looks like I have about 4 cases here. If I look at my descriptives for my student-ized residuals, I see I've got a minimum of negative 4.34, right? So these are going to be very, very low residuals. These are going to be cases where my expected social support for these cases is much lower than what I had predicted, right? And so these are cases that I'm missing pretty by quite a bit on. We've got 335 people in this sample. We expect to have, I mean, that's a large sample. We're expecting some values to be sort of out there. Nothing too much on the top end, but again, if we look at our data, we've got a lot of people sort of there at the top, so we're not doing that too bad, but we're predicting some or missing some of these cases that are lower than we would expect it, right? So again, right now, I don't know if they're problematic, but I'm going to write them down and make a note. Probably I'd sort of maybe target this collection of 4 folks right here, kind of take a look and see what's happening with things. Okay. So again, if we go through and take a look, cases 291, 292, 364, these are all cases that are objectively large in terms of standardized space. They're anywhere from 3.5 to over 4 standard deviations away from the mean. We know that's sort of big, right? So something to go through and keep an eye on, okay? Again, our observed value lower than predicted. Our models overestimating our perceived social support for these cases. So wanting to take this all into consideration, not just writing down numbers, but also thinking about what does this mean? What is my model doing in these situations? Okay. So these are cases that are weird in Y space. All right. Same thing in Stata. Just putting it out there. Okay. So people see what we got in terms of our discrepancies, how we're thinking about those cases. Okay. We're also going to take now, switch over and start thinking about leverages. Okay. We're typically looking at a leverage using leverage or hat values. Okay. And again, what we're doing here is we've switched over to looking at things in Y space. We're looking at unique cases within our set of predictors. These are often multivariate outliers, but as we'll see, if we start to have individual cases that are quite large, even on, or quite extreme, even on one variable, we can start to pick these up with our leverages. Again, these are folks that are strange in terms of our predictor space. Okay. Again, our leverage mathematically, this is just an index of the distance between that individual case and the centroid of predictors. Again, centroid is just the mean of all of the mean, is the space out there in multivariate sort of space where that's the mean of all predictors, right? It's easy to see in 2- and 3-dimensional space. When we get into 4-dimensional space, then things get strange. But if we take the mean of everybody, right, on all our predictors and sort of see where these different points are, that distance is going to be what we're calculating as our leverage. Okay. Now, leverages, as we're going to calculate them or request them from Stata or SPSS. In Stata, our standard leverages are going to range in value from 1 over the number of people in our sample to 1, with a mean of the number of predictors plus 1 divided by number of people in our sample. Centered leverages, this is what SPSS produces. It's a little bit different. These are going to range from 0 to 1 minus 1 over the size of the sample. Okay, so the upper and lower bounds for your leverages are going to depend on the number of people you have in your sample, the number of predictors that you have. Okay, generally, we got leverages that exceed 2 times the number of predictors plus 1 divided by the number of people in sample as a minimum threshold for further exploration. We'll bump this up to 3 times the number of predictors plus 1 over n for smaller samples. This is for standard leverages. For centered leverages, which you'll be looking at in SPSS, it's going to be 2 times the number of predictors over the sample size, or 3 times the number of predictors over sample size to look at these, right? This is giving you, again, general benchmarks, okay? These are things that, like, these are benchmarks that are going to say, hey, maybe I'll sort of eyeball this or think about this or give me some benchmark for identifying magnitude. These are not hard, clear cut. If you ever say, I threw this person out because they exceeded this benchmark of, you're doing it wrong, okay? There's just a lot of information that has to come to get bear to think about, what am I gonna do? Is this a problem? Things along these lines, okay? Also note, as we'll see in our examples, this is a minimum threshold. What's gonna happen is these thresholds are gonna identify cases. You may end up with 10, 15 cases that exceed this threshold. Now, you're obviously not going to indiscriminately throw out 10 to 15 cases, right? But it's just telling you how hot is hot, right? Like, oh, this is kind of hot, but hot is relative to where I'm at. Like, sort of, yeah, this is uncomfortable hot, but this is scorching hot, sort of out there in these couple of cases. Again, putting things into context here, okay? Again, with all of these, as you start to go through, if you do identify cases that are potentially problematic and you do elect to throw those cases out, what you then need to do is start from the beginning and go through and reevaluate this, because again, we can get masking things where I have a weird case, but it's masked by an even weirder case. Once we get rid of that weirdest case, now the weird case is pretty weird relative to the rest of the sample. Again, what can happen if we're not doing this carefully and mindfully is what we can do is just start chopping things off until we've substantially reduced our sample size. So we need to be careful and sort of thoughtful in what we're doing with this and understanding why these cases are strange, okay? So for this sample, again, box plots, histograms are nice ways to go through and plot these out, okay? What are we saying in terms of leverages here? So here, because we're doing this in SPSS, we're going to use 3 times the number of predictors divided by the sample size as our criteria for things that might start to catch interest. And if we do this, we get 9 different cases that are exceeding these leverage values, right? That seems like a lot until I start looking graphically at about what's going on. And if I'm looking at this graphically, what am I seeing, Katie?
That there's a positive skew. And it seems like 276 is really pulling.
Yeah. Now with these, because you can't have, I mean, you have a minimum value for your leverages, and so those you'll always have a positive skew for this. So we're not so worried about the distribution of these cases as so much as what's happening out here in the end. So 276 is way out here, right? But then we have some other cases that are kind of still on that edge. If we go through and we list all the cases that are exceeding our threshold, we get 9 of these. But the question is, what do we then do? How many of these do we explore? Sort of what's the idea? How do we go through and approach this, right? Again, same thing. If we go through and identify these cases in Stata, same type of thing that we'll get here. We'll see that our criteria are a little bit different because these are standardized leverages versus centered leverages. But again, the same cases are kind of falling out, okay? Now, what we're going to do is, if I go through, and you can do this in SPSS, it just takes a couple extra steps. What I've done here in Stata is ask Stata to give me the 5 largest leverages from this set, okay? And this is giving me, and I'm asking for the leverage value, the subject number, and then our various predictors, right? So here we have leverage, our largest leverage, 059. This is case 276. This is the one that's hanging out right here, right? And then subsequently our sort of next sort of highest ones, okay? But anytime we want to go through, we go through and we identify leverages. our high leverage values, cases we want to explore further. What we want to do is then understand what's making those, what's causing those cases to be weird in X space. This is an incredibly important piece of things. And so if I go through and if I ask Stata to give me just descriptive statistics for these cases, right? If I go through and I take a look at, we'll just point out 276 here, right? So we can ignore MSPSS because this is our outcome. Outcome doesn't impact your leverages. That's a Y space thing. But if I look at my AAQ, right? This person has a value of 16. What's the mean of AAQ for the sample? Just here on the slide. 21, okay? Is 16 weird relative to 21 with a standard deviation of 9.8? Not really. Okay, so that's looking fine. We got Bass reward here with a score of 11. Here, the mean is 17 with a standard deviation of 2 is 11. Strange. Yeah, it's low, right? So we've got a low Bass score. BIS here is 12. We've got an average, a mean for the sample of 21 with a standard deviation of 3. That's really low, right? And then a score of 66. So we've got a score of 45 here. So we've got standard deviation of 7. Yeah, so we've got a combination here of really high NOS. This is going to be sort of reluctance to engage social support networks combined with a really low BAS and a really low BIS. So behavioral inhibition and reward seeking, stuff like that. So we've got someone who's reporting a combination of low reward seeking, but low like neuroticism stuff, but really high on willingness to or reluctance to engage with other people. It's just a weird combination of variables that doesn't fit sort of what we're generally seeing in the model, okay? And so what we want to do with these leverages, with these multivariate outliers, what we want to do is go through and say, how do we go through and identify what variables that these, what variables are these folks strange about on, and then start thinking about, like, does this make sense given what I know about this phenomena, right? This is going to start to become important when we start thinking about, do we keep this person? Do we throw this person out? Is this person part of the population of interest? Are these valid scores? Because sometimes you're going to get combinations that literally cannot exist in the universe, right? That suggest that maybe that person is not taking things seriously or didn't understand instructions or things along those lines. So we're going to spend a lot of time going through and thinking about what's actually going on with stuff.
So how do you know if something is strange? Like I know some situations like it would be pretty obvious, but did you just know, like, because when you're out on the board and you're saying like 17, is that strange? Like I didn't know. So like, do you just need to know the variables?
Oh no, I mean, just sort of thinking about the distribution relative to sort of the general sample. So this is just the means and standard deviations for the whole sample, right? So if the average score in the sample for BIS total is 21, right? For this sample, the average score is 21 with a standard deviation of 3, right? So if I get 2 standard deviations out, let's call that a value of 8. We're now 21 minus 8. We're at 13, right? Person's score here is 12. So we're over 2 standard deviations below the mean with this, right? And so just by definition, that's kind of a strange score. But when we combine it with, when we think about behavioral inhibition and activation, right? These things, and this is sort of just understanding, these are things that sort of probably kind of go like this. And I've got 2 that are down here. That's starting to get strange, right? So yes, a lot of it will be content area, but some of it is just empirical. Like, yeah, this person is really low on sort of these types of things. So again, like anything else, a combination of looking at our statistics and then thinking about, like, okay, within the context of the constructs that we're measuring, what does this mean? Okay. Yeah.
Maybe research, but top one is just our extreme values, and the bottom one is average.
What's that now?
Like the top one is like our outliers, and the bottom one is average.
Yeah,
Right, so
yeah,
that's what we're gonna
yeah,
do.
yeah, yeah.
Okay,
And
cool.
this is just, I can ask these in Stata and it just kind of sort of drops them in. Probably what we'll do in the example here is we'll just kind of sort the variables and say, okay, well, here's this one and this is so just kind of look there. All right, so yeah, we've got a case that's got a high NOS score with low AAQ, BAS reward and BIS. We're going to go through a procedure where we can go through and actually test to see, all right, what are the cases that are coming up and causing this to be problematic? We'll walk through how we would do that in SPSS, but sort of this is the general idea. Not only do we don't just want to identify multivariate outliers or large leverage values, we also need to go through and do a dive into say, why is this weird? Like what's causing this to get flagged with things? All right, questions about the leverages? All right, for influence, okay. Again, as I had said before, I can have a high leverage and it might not make a big difference. I can have a high discrepancy, may not make a big difference. But just one or the other isn't sufficient to sort of have a huge impact on our model necessarily. It can, it doesn't necessarily mean it will. Influence is a combination of both leverage and discrepancy. And the idea behind an influence, a high influence value, this is a value that's going to, if it were removed, have the potential to impact the model, individual coefficients and things along these lines, okay? This is where we start worrying about like, is this person does having this person in our sample start to screw with our estimates, okay? Because if you have an entire model or an entire effect that's driven by one or two people, that's not a replicable effect, even if it's doing things that you would like. We start to worry about the generalizability of our model if there's just one or two weird cases that's driving things, okay? A couple different measures of influence. Cook's D. This is looking at the difference in our coefficients for our full set of difference in coefficients for the full set versus coefficients if we were to exclude the sample or the case, right? So for this case, and it's just one number, right? But the larger that number gets, the greater the influence of that case on things start to change by quite a bit relative to the set with that case in or out. Threshold for Cook's D, general recommendation, anything greater than 4 times sample size minus the number of predictors minus 1, again, may warrant further investigation. I cannot stress this enough. Just because it doesn't mean it's problematic. This is just all pointing you towards things that say, hey, maybe I'd sort of take a closer look at this, okay? Cove ratio, this is looking at sort of the impact of a case on the width of a confidence bound, okay? Remember that case. We got a YX, right? And if I'm just looking at this set of cases, I've got maybe a line that looks something like this, right? But let's say I have a case out here that's right there. Now all of a sudden I've got something that's much tighter and much stronger and starts to reduce sort of my estimated error around things. Not because it's bad or it's necessarily falling far outside of my predictive level. It's just something that's causing the model to think this is a much clearer, stronger relation than what it would be if we're just kind of looking around here, right? So our Cove ratio is looking at the impact to which an individual case starts to change our presumed level of precision of our estimation. If I have values that are greater than 1, it sounds like it's improving it's indicating that this case is improving the precision of estimation. If it's low, it's decreasing the precision of estimation. And we might say, well, why would we worry about increasing the precision of our estimates? So you're always harping on us about precision of our estimates. This is the reason, right? Because we've got one case that's making this model look a lot better than it should be, right? And so we need to be concerned about this thing. So again, for cove ratio, anything, so we've got kind of a, if we take the absolute value of covariance ratio -1, if that is greater than 3 times the number of predictors plus 1 over sample size, could warrant further investigation. We're going to focus mostly on Cook's D just to keep it simple, but just wanted to throw this out so you kind of know different metric, kind of what's going on with this stuff. So if I go through, if I look at Cook's D cove ratio for this set, and here I'm just in SPSS plotting out box plots, right? I've got a total of 17 cases with Cooks that are exceeding my sort of threshold, 25 cases with our cove ratio exceeding. This is what's going to happen. Like I said, you're going to get cases, a lot of cases that generally will fall beyond your expected values for sort of further investigation or consideration. But again, Sam, if I'm looking at this in terms of my influence values, if we're just looking at Cook's distance, which cases might I be most concerned about? What's that? Yeah, for Cook's distance. Yeah, right. 276, 292, 380. These are all ones that are kind of hanging out. I mean, these are all probably not great, but these ones are the ones that are really sort of kind of looking like they might be problematic, right? If we go through in Stata and take a look at the thing, in Stata we can request what's called a drop line plot, and this is kind of nice. It just kind of labels everything up. It's just a different way to go through and say, okay, boom, boom, boom. We've got 3 of these towers that are hanging out above everything else. It makes it a little bit easier to go through and see. We can also run a histogram and see that, yes, these 3 cases are all kind of hanging out here. So just a little bit different way to take a look at things. So what we would probably do is want to go through and sort of investigate maybe these 3 additional cases here. All right. So these are some basic things that we can go through and take a look. But regression diagnostics are an entire field of it, in and of it to themselves. Like it's a whole area. There are many, many more types and strategies and things that you can go through and take a look at. For example, if I want to look at linearity, I can run a scatter plot of my residuals versus my individual predictors to see if there's weird nonlinearities there, if I have some concern. If in my overall residual plot, I see that there's something that's looking very non-normal and I need to try and identify where that's occurring, maybe this is something I go through and take a look at, right? Other measures of influence, DF beta. What this is doing is looking at the inclusion exclusion of a given case on coefficients for individual predictors. So not just the whole model as a general index. I can start to get in more nuance and say, with the inclusion or exclusion of this case, what does this do to this parameter? Have to watch out because this can encourage futzing with data and sort of keeping or getting rid of cases just because we don't necessarily like what they're doing. But if we need to get a sort of more in-depth diagnostic, that's an option. Independent error. This is if I have concerns about like autocorrelation or sort of cases being correlated with one another, I can run an index plot of our residuals that's looking at sort of, you can start to see places where you have cases that are starting to group up, right? Like if I have case 1 to 20, right? Or let's say 1 to 100, right? And what I find is that in terms of my residuals or how far I'm off, cases like early cases, like 1 to 50, my residuals are pretty low. But if I'm looking at this, as I start to get farther along in my cases, my error starts to get more and more and more. Now, if I just looked at in a scatter plot, I wouldn't see it. But if, let's say early on, I have very low residuals, and later on in my data collection is indexed by the sort of the participant number, I'm getting much more error. What might that suggest? We've got a problem because we have error that's associated with people who were collected earlier in the experiment or the study have very low error. People who are later in the study have much more error. What might be a situation where we might see something like that? If we get experiment or drift, early on, people are trained up, they're doing pretty well. But as the experiment goes on through the semester, Robert, as you're going through early on, everybody's trained up on your thesis and doing well. As we start to get farther and farther and farther along, people start to get pretty loose, and sort of coding gets bad and things along those lines. And so now all of a sudden, this creates a problem because the errors of participants 4 and 5 are much more tightly correlated than the errors of participants 98 and 99 relative to one another, right? Or relative to sort of cross things like that. This can be a way to start to look at independence of error, even in cases where we don't have or shouldn't have autocorrelation going on in terms of things. Specification error, we can start to look at different plots after we include or exclude different predictors. And then combination plots. These combination plots, we're going to work through a couple of these. These are really nice because we've talked about leverages, discrepancies, and influence points all separately. But these combination plots start to put everything together in kind of a common plot to start to identify cases that are potentially problematic. Again, this is a plot that we can request in Stata. We've got our squared residuals on the X and our leverages on the Y. What we would look for are cases that are hanging out up in this upper quadrant right here, because that would indicate a large residual value and a large leverage value. If we went through and we identified individually and then found people kind of hanging out up here, that would be potentially problematic. We say, hey, these are folks who are having a potential to really impact our plots. Okay, different one. Again, this is just an example from Stata. Here, we've got leverages on the X, studentized residuals on the Y, so we just kind of flip that around. But now what we've done is ask the program to draw circles around individual cases with the scale of that circle relative to the size of Cook's D. So if we want, so what we're worried about here are cases, again, that are falling in that upper right-hand corner or that lower right-hand corner, but then also the size of the circle is telling us how big the sort of that Cook's D value was for that. So Josiah, if we're looking at this plot right here, which cases may be the most problematic that we would want to take a look at? 276 for sure, right? Yeah, 380 maybe, right? So we've kind of got this hanging out down here. You know, yeah, 292. So we've got a big influence, a larger Cook's D here, but really in terms of our leverages and our studentized residuals, it's actually not looking too bad. Things like this can start to help put things into perspective to think about like where's our stuff hanging out at, right? But this one in particular, probably want to go through and take a look at this. Now, the other thing too, we've got 360 some people in this. So that's a pretty heavy sample. Someone would have to be pretty out there in order to really impact that, but still worth taking a look. Yeah.
So I'm thinking about like extreme values and outliers and just like dealing with them, like if they are causing a lot of problems. And I know that this is different than missing data, but I know like what issue with missing data when you delete the value but not the entire case could be that, I think I'm saying that correctly, but an issue could be that it causes issues in your analyses, like your analyses will skip over where there isn't data and then pull data from somewhere else. So like with outliers, if you do delete an outlier, could a similar issue happen?
Well, for these analyses, if I delete a value, that case is out of the whole thing because I can't have it. I need for our standard regression, for OLS regression, you need full information, right? If anybody's missing a score on anything, they're out, right?
Okay.
So, and I would say if you've got someone that's risen to the threshold where you're confident in throwing them out, whole case just needs to go. That's a weird person for whatever reason. There's lots of reasons people can be weird in our data sets, right? So I would do that. Now, if you're running a full information model or something like that, you could start deleting, like, oh, I don't like this value. But that seems like the worst of both worlds because you're saying, I don't like for this specific variable or this specific time point, I don't like the value that you have. I wish it were something different. It's not, but I want to keep you in because I like the other things that you're doing, but not this. That starts to get problematic, okay? Unless you know, like, well, we had an equipment breakdown that gave us a weird reading for this person at this time point. So we pitched that because it's not valid because we had an instrumental thing going on, right? But otherwise, if you've identified somebody, just go through and get rid of the case. And if you were running these analyses with the sizes of samples that we should be running them, whether or not you lose a couple of cases shouldn't be a big deal. Where it starts to become problematic is if we don't understand what we're doing with this and just cutting out back, oh, I had 20 people with Cook's D above this and just wiped them all out. One, you just lost a chunk of your sample. Two, when you go through and you rerun these analyses, because after you cut anybody, you need to go back through and take a look at it again. You could find another 20 people now that are now above the threshold. So you just have to be careful and mindful about that. Okay. Throughout all of this, if you go through and exclude anybody, you should be able to very clearly say in your papers or your theses or dissertations, we ran screenings, we found sort of a handful of cases that were X, Y, and Z. Specifically, these cases were sort of whatever happened did not appear to be sort of valid responses, things along those lines, and as a consequence were removed. Reanalyses, I failed to identify any additional sort of problems or things along those lines, right? So you should be able to very clearly state why you threw those people out. And that explanation shouldn't be because some value exceeded something. Okay.
So with the outliers, it's different than missing data in a way because if like there's any, it's kind of looking at the whole data set together versus just like the variables of interest that you're looking at.
Because you can have an extreme value in univariate space that works perfectly fine within the context of this, right? And you can have data bivariate cases, bivariate plots that look strange and heteroscedastic sort of in that, but when you work at them in the context of your residuals, everything looks fine and perfect, right? So again, this is what makes this hard. There's no one way to say if this, then that always. You have to kind of know what you're looking at and pull it together to make sound decisions. Other questions? All right. We can run these combination plots in SPSS as well. Here, we're looking at our leverages by our studentized residuals. It's similar to this one. We're just reproducing this in SPSS. SPSS won't give us sort of Cook's D by size with this. But again, you can still see this case hanging out right here. That's going to be problematic. You can attach here, you can attach labels to these cases, but no, everybody look at me into my eyes. If you do this, this is not your subject number or your ID number. This is the position of the case in the set at the time that you run the analysis, right? So this little label up here for 335, this isn't case 335. This is just the case that's second to the last in the case because I probably sorted it by Cooks or something like that. And this was the second largest. And so it's going to flag this as 335. You can go immediately to your file, look at whoever's in row 335 and identify who that is. But these are not participant numbers. Okay. There's no way to actually do that. You can flag it, identify certain cases, and we'll do this, but just make sure, because if I go through and resort this is going to be a completely different number, just given where this case is in my set. So when I'm doing this, what I like to do is just have a sheet that I'm going through and kind of make a tally. What are the cases that I identified as problematic as I was going through and looking at things, right? And so if I go through and look at, I've had 207, 258, 260, and 276 all come up as high leverages, as well as 380, right? 291, 292, and 364 had high residual values influence. Ones I flagged, 276, 292, and 380. But really, if I'm looking at this, it's looking at 276, a really high leverage. Influence was high. Residual wasn't bad, right? It's not like this is, I'm really necessarily, my model missed predicting this case, but if I look at the combination plot, if I look at my influence value, if I look at my leverage, this is just a weird person who's a repeated suspect that keeps coming up again and again. I might go through and want to say, oof, what do I want to do with this person? Do I want to keep them? Look through not just the records for this analysis, but also the full stuff, right? This is why it's always good when you're running, again, Robert, if you get someone who comes up in your analyses who's really weird, go back through your tracking sheet and say, was this person paying attention? Did they try and get a fist fight with the RA? Did they do something else weird? You know, I don't know what's going on, because oftentimes you go through and find like, yep, there's a reason that person was strange, or they showed up 30 minutes late and demanded to participate anyway, and then rush through it in 2 seconds, right? Like these are the types of things you can often go find when you're looking at stuff, okay? And that just helps you be confident that, yeah, I'm throwing this person out for a good reason if you do in fact decide to do that, okay? All right. Okay, some final issues, multicollinearity. Remember that in our regression models, we're looking at the unique contribution of our predictors on an outcome. That unique contribution is likely to decrease as our predictors get more and more highly correlated, okay? When I have high collinearity, my regression coefficients start to get unreliable, the sampling distribution. The point estimates are unbiased. Like the actual number is fine. What happens is standard errors start jumping around, right? And if we get unstable standard errors, and those standard errors start to jump around, even with small changes to the data, right? I sort of maybe throw one case out, and this thing goes from being a strong predictor of an outcome to not at all a predictor because my standard error started jumping all over the place. It starts to become problematic, okay? So the primary concern with collinearity is not that our estimates are necessarily compromised, but the standard errors are compromised. And if the standard errors are compromised, I can't make strong assumptions about the precision of my estimates, and then that starts to become problematic, okay? For bivariate cases, general rule of thumb for problematic collinearity is if you have variables that are correlated 0.9, you need to be concerned sort of way before you even get to anything that's correlated. But if you have predictors correlated 0.9 with one another in your model, you're measuring the same thing multiple times. Like the measures have different names, but it's essentially measuring the same thing, okay? Some simulation research suggests that variance inflation factor of even as high as 2 starts to become problematic, right? Remember that variance inflation factor is giving us a sense for sort of the impact on the standard errors, right? You've got a 40% increase in standard errors relative to a case where you would have uncorrelated predictors if you have a VIF of 2, okay? So if you do have cases where you have lots and lots of collinearity, one, you should address that conceptually on the front end, but if for some reason you have to have it in there, be very cautious about the standard errors in your statistical tests and things along these lines. Okay. So in SPSS, This is pretty easy to do. You can go through and take a look at your bivariate correlations, making sure that none of those are sort of too highly correlated. But in our diagnostics, remember, we can have problems with multicollinearity involving combinations of variables. This is where things get a little bit tricky, right? Things that you may not catch in just the bivariate correlations. And so what we can do is we can go through and ask for collinearity diagnostics. Here's our tolerance values. Here's our variance inflation factors. Tolerance values of less than 0.1, variance inflation factors greater than 10 for any of these variables are all going to be problematic. But again, if you get within 10,000 miles of either of these values, you need to start sort of being concerned that you have conceptual redundancies in your model. Okay. So these can be helpful in saying, like, is there identifying whether or not we have problems? But sometimes if you have collinearity that's a function of multiple variables, it can be hard to determine what combination of variables is sort of being collinear with some other. This is where we get down into our collinearity diagnostics. Really what we're looking at here, if you have a condition index, which is right here in this column here, condition index greater than 30. And so these are condition index greater than 30 combined with a variance proportions. It's over here for individual variables that exceed 0.5 on 2 or more. That's suggesting that we have problems with sort of whatever combination here. So here we do have a variance inflation factor, or a condition index that exceeds 30, right? So we've got one that's 33.2. But this is the last one. Your last condition index is always going to be high, just the way that these are calculated. But then what we're going to go through and take a look at then is my variance proportions. And here, BAS is 0.66, but there's nothing else. My AAQ, BIS, and like none of these things are exceeding greater than 0.5. So there's really no concerns here. And so if I went through and take a look at my variance inflation factor, these are all, none of those exceed 2. Lowest tolerance is 0.6. So there's no reason to even worry about anything down here. This is saying I don't have a problem with collinearity. I have correlated predictors, but I don't have a problem with collinearity. So yeah, this is just where we're taking a look at that stuff. And then again, in Stata, sort of commands to look at tolerance and variance proportions and things like that. All right. So our summary: accuracy, plausibility, missing values, univariate distributions, univariate outliers, linearity of bivariate relations, and initial screening for heteroscedasticity. But here we're going to look at error distributions, discrepancies, multicollinearity types of things. This is all going to come out of our regression diagnostics. Okay, cool. People ready to jump into SPSS and actually start playing around with this to see kind of how we go through and produce some of these statistics? Feeling good about this? All right, let's do it. So what we're going to do is open up this exercise, this regression set. Okay. And what we've got here is an example that we're going to do a lot of work with. What we've got is we're trying to predict role functioning, okay, in individuals who have been involved in serious motor vehicle accidents, right? And so our predictors in this case are going to be a measure of PTSD severity, a measure of chronic pain, or just pain severity, and opiate use. So we're going to throw a dichotomous predictor in here, whether or not people are or are not taking opiate medications, okay? So PTSD ranging from 0 to 136, pain 0 to 6, opioid use, no, yes. Also, for your dichotomous variables, when we're working in a regression, 0 is always your reference. Okay, so don't code things if you got categorical variables, don't code them 1, 2. 0, remember that 0 has a special place in regression. 0 is a magical number in regression. So always have your reference values coded to 0, 1, that dummy code as opposed to 1, 2 types of things, because otherwise it can start to screw things up. And then we've got role functioning. Okay. This is an indicator of adaptive functioning. Higher scores are indicating greater functioning, range 0 to 100. Okay. So what we're going to do is we're going to set up a regression model where we're predicting role functioning based on the best linear combination of pain, opioid use, and PTSD. If people have a sense for the set for what we got going on. Okay. So just to save some time, I mean, because this is not sort of news to anybody with things. Okay. So again, we're just going to go through, use our standard approach that we would normally do. And here, go through and sort. We don't have any missing values, right? So we don't have any missing values in our data. And so we're going to ask for frequencies for our opioid use and then descriptives for our continuous variables. If we go through and take a look at opiate use, we see we have 101 people without medications and 100 people with medications. We're pretty good there. We've got a nice balanced dichotomous variable. So half of our sample are on meds, the other sample aren't. So this is pretty good, right? I'm feeling good about this. I'm going to ask for my descriptive statistics, right? Anything going strange with my descriptive statistics here, Allie? Anything strange with the descriptives? What's that?
I mean, there's,
Yeah, for my role functioning variable, right? If I go through and I take it like ranges, everything's falling within value, so I'm fine. But if I look at my role functioning, I've got a skew value of 2.26, kurtosis of 4.17. That's going to sort of flag back, okay, I maybe have some stuff going on with my outcome variable, right? So, and if we think about this, if these are individuals coming in for PTSD and pain to a research clinic, where are we expecting role functioning to be? Very high or very low? Probably pretty low, right? I'm in pain. I've got accident-related trauma stuff. My functioning is probably going to be pretty low, right? So, okay, we go through, make a note of that, and then we go through and we run our examine stuff to go through and take a look at our distributions. PTSD, looking fantastic. This is nice and normal, right? Box plot, we've got one person hanging out there, but it's nice, it's symmetrical. That's about as nice of a figure you're going to get with actual real data. So we're pretty happy with that. We go down through, we take a look at our pain scores. SPSS has been this kind of weird, but overall, are we too concerned about the distribution of pain severity? What do you think, Matt?
Not too much. Looks like there's a little bit of negative skew.
A little bit of negative skew, right? So if I'm thinking about this, it's suggesting that the majority of my people, whether or not they're on medication or not, they're reporting some level of pain, right? And sort of trending towards higher levels, but nothing that we're too concerned about. Okay. Then we get into our role functioning variable. This was the one where we had a skew of 2 point something, kurtosis of 4 point something. What's going on here? What do you think, Josiah?
What does 0 represent?
0 is the bottom of the functioning. Is range on this, as we sort of reported it, was 0 to 100, with 0 being the worst level of functioning, 100 being best functioning. What's happening with this?
So we have a lot of people that are not functioning very well.
Yeah, yeah. What boy, what's going on with this box plot?
Well, I noticed that the readings are all in 25. So it looks like you have majority of your guys with 0, and then further out you go, you have 25, 50, 75, 100.
Yeah. So do I have a real continuous variable here? No, I don't. I have an ordered categorical variable with 5 categories in this, right? I have, looking at my box plot, my median, my first quartile, and my third quartile are all zeros. And so basically anybody who doesn't have a value of 0 gets thrown way up at the top, okay? Rachel, we were talking about some of your data and some of the same types of things happening, right? This is a big concern, right? Because one, yeah, it's skewed. We can address this thing, but we've got a bigger issue with level of measurement here, right? If we look, you say, oh, it's scores range from 0 to 100. Sure, but in 25 unit increases. And so, yeah, I don't really have a continuous variable here, okay? This is going to make everything that we do from this point on like super, super ugly, okay? But right now, it would be hard to sort of make a strong argument for just ignoring this and moving forward with this and treating this as a continuous variable, right? So one of the things we might want to do is think about, well, maybe what we'll do is try a transform on this, okay? So what we're going to do is we're going to go through and run a natural log transform. Now, natural log transform is nice because in the context of regression, the natural log transform retains some interpretive properties that we'll talk about a little bit later. But what I'm going to do in SPSS is I'm going to go through and I'm going to go to transform. I'm going to go to compute variable. I'm going to create a new variable. I'm going to call it ln roll. And I'm going to make that new variable the log transform of my outcome here, okay? Now, if you go through on this function group, what I want to find is the natural log. And if I click on arithmetic, it's going to go down through and give me a bunch of different functions down here. And so I'm going to go through and find ln. This is my natural log. Double click that. And I'm going to take my roll functioning variable and drop it into that. Okay, pretty easy. What's the one thing I need to be careful about with this? Because if I run this, I'm going to get a bunch of errors. Yeah. 0, I can't take the natural log of 0. I can't take the logarithm of 0. It's undefined, right? So what am I going to do to address this?
Going to add 1 to each one of the scores for roll effects.
I'm just going to say roll functioning plus 1. The scale doesn't matter, right? Like the numbers are arbitrary. Whether the low value is 1 and the high value is 101 makes no difference, right? But what I can do is I can take the natural log of 1. And so what I'm going to do is I'm not going to take the natural log of roll functioning. I'm going to take the natural log of roll functioning plus 1. I'm just adding a constant to every value that's going to allow me to go through and perform this transformation. So the same thing is going to happen if you have try and take a square root transformation or things along those lines, always being aware of, or if you say have a variable that ranges from a negative value to a positive value, anything that happens to fall on 0, you're not going to be able to, so you need to be thinking about the scaling of your variables before you start applying transformations, because otherwise, and you'll know because it just won't calculate them, and then you have a bunch of blank values. You're like, why are there blank values? Like, oh, all those were 0. I have to go through and sort of do some stuff. Okay, so what we're going to do is we're going to go through. I'm going to paste this here, and you can see the actual command is pretty straightforward. Nothing terribly complicated there. We're just going to run this, and now I've got a new variable that's the natural log of roll functioning, right? Where most of my values are still 0, but I've gone through and changed things out, right? So what this is doing, any log transformation, my cases did run from 0 to 100. That's a pretty big space. when I run my natural log transform, I now have values ranging from 0 to 4.62. Okay. It didn't do anything special. All the people who had values of 100 still have all the same value. Everybody who had 75 still has the same value. Same thing for 50 and 25. I mean, that's just how math works, right? But we just brought this in, right? So it doesn't fix the fact that we have a categorical variable, or the fact that we've got a categorical variable that's kind of ugly. It just makes it look a little less ugly for this analysis, okay? And so now if I go to analyze descriptives, click this and look at my skew and kurtosis values for my natural log. Pop this up because it's easier to see. Okay. So Brittany, is my distribution or is my histogram and my box plot any better than it was before? No, it's not, because again, at the end of the day, I have an incredibly skewed distribution that has only 5 values in it, right? So my plots don't look any better, right? But if I go down through and I take a look at my, if I take a look at my skew and kurtosis, are those looking better? Oh.
Yeah, it's a little better. I mean, it's a little lower for skewness.
Yeah. I mean, skew is not 2.4. It's now 1.6, which is still pretty skewed. Kurtosis is considerably better than what it was before. So is this a great solution? No. Is it better than what we started with? Probably. Do we have a transform that still maintains some interpretive properties? Yeah. So what we're going to do is we're just going to decide to roll with this and then talk about other options that we would have sort of at the end. Okay. So people see what we did there and understand why we made that decision. Okay. And it wasn't without thinking about it, what the consequences are, but what we're trying to do is sort of do that in a situation that still gives us a way to think about and make interpretations about our data, even once we've made the transform. Yeah, Rachel.
Would transforming the data, or would there ever be a situation?
Okay, question is there a situation where you would transform the data and then it changes the results? Absolutely, it can, right? And so this is what you need to be thinking about probably in terms, and you've got 2 philosophies that are pretty distinct when it comes to regression or analysis in general in terms of screening types of things, right? There's one philosophy that says you choose, and once you've chosen based on the best sort of information that you have, then you run with it, and that's what you've got, okay? And this is an idea to prevent shenanigans where I run 7 different transforms and try and figure out which one sort of does, and you can get weird. I was working with Ryan on his dissertation, and sort of he has a suicidal ideation measure that's sort of super skewed, and was looking back through a paper and someone had like 3 times square root transformed the outcome, which is mind-blowing to me, right? Each time you do it is start to bring it in a little bit more, but I don't know, that's hard because I don't know what that outcome is anymore. That's not like a real actual thing, right? But sort of it's tradition in certain areas and things along those lines, right? But sort of the one hand says you sort of make your decision and that's your bed, you lay in it, and sort of that's what it is. Other tradition is sort of going through and saying, okay, let's go through, this looks really bad. What happens if we get rid of it? Yeah, it changed the whole thing. Okay, now this is a thing. Or I went through, looked, decided that maybe this was a case I was going to get rid of. If I get rid of it, actually nothing really changed. So just leave it in there, which is kind of my approach, right? Because then I don't have to try and explain why I'm screwing around with stuff or throwing people out. If it doesn't matter if the person is in or out, even if the case is super ugly, I'll just leave it in, because then that simplifies things, right? Where we start to get into problems is if things start to change and the results and the particular effects that I have start to change based on what decisions I make, then that starts to get tricky, right? Because they might be changing because the person that I threw out or the transform I used was good and they needed to be thrown out, and I have a much more generalizable model. This is a good thing that I've done, right? Or it could be I'm just capitalizing on sort of procedure specific stuff, right? And if I've got a result that is contingent on 1 or 2 people being in there, or a result that's contingent on what specific, whether I use a natural log or a square root or an inverse or something like that, I start to worry about the stability of that and sort of need to think and would want to think carefully about sort of why I'm making choices and sort of, or sort of the, how much I'm going to say, oh yeah, this is a real effect that's probably going to be found that captures something that's going on out there in the universe. So yeah, all things to think about, and just want to have kind of a game plan, know what you're doing and why before you just jump in the middle of stuff.
So I guess to summarize, if before you transform it, there's a significant result, I know that, like, significant,
Yeah.
throw everything on, and you transform it, and it's not significant, that's probably evidence that the result that you found was because of like a case that's nuts.
Or a strange sort of feature of that data, right? I mean, because if I just ran the model and things are working well, and I'm like, oh, maybe I'll transform it and it doesn't, what I would start to worry about is maybe that it's the folks on the tail that are driving that outcome, which maybe, right, if we've got some people who are extreme, but I would start to be worried unless I had a really big sample that was kind of populating that tail out, that really it's those folks who are sort of there on the margins are driving that thing. And if I actually bring them in a little bit with a transform, which is a reasonable thing to do, and now that thing, whatever effect that I was wanting to interpret kind of goes away, I would think about it, right? In terms of robustness for things. Yeah. All right, cool. Let's do this. Let's take a break. Let's come back, be back here ready to rock by 3:40, and we'll jump into additional stuff, sort of moving forward with these analyses. There we go. Okay, cool. So up to this point, we identified a problematic distribution. It's not really so much the distribution, it's the level of measurement with our outcome variable, right? Hopefully we would have sort of recognized that beforehand. We didn't. The data are what we have, and so this is oftentimes what ends up happening is sort of choosing between a handful of sort of low desirability or low desirable sort of approaches, but we're just going to go with the natural log transform here and sort of roll with that. Okay. So once we've gone through and done that, what we would do is go through, take a look at our standardized variable or standardized scores for our cases here. And if we go through and we do this, Elizabeth, do we see any concerns with extreme values sort of based on our Z scores here? Yeah, probably not. I mean, we've got something that 3 standard deviations below, 3 standard deviations above, but not something that we're going to be overly concerned with, probably, again, given the size of the sample. Okay, so we're feeling okay, probably nothing much going in the way of extreme values there. Okay, now what we need to do next is we want to go through and take a look at our bivariate plots. Okay, what we need to do is look at scatter plots, and what we're looking for here is linear, making determinations on linearity and homoscedasticity assumptions. Remember that because we violate that fixed effects assumption of our regression analyses, we're okay so long as our data are multivariate normal. And we're assuming that our data are going to be multivariate normal if we have all our variables are normally distributed, which we're already sort of violating that a little bit. And all of our associations, bivariate associations are linear and homoscedastic, right? So what we're going to do, because it wouldn't be terrible here because we don't have that many predictors, but it can get pretty intense if you get a bigger model. So what we're going to do is we're going to go to graph, we go to chart builder. We're going to go to scatter dot, and we're going to go down here to scatter plot matrix. Drop this into SPSS, and now what I'm going to do is I'm going to take pain, opiate use, not opiate use, opiate use out. Pain, opiate use is a dichotomous variable, so it's often not useful to put in here. PTSD and the natural log of role functioning. Drop that in there, okay? And then you hit paste, I'm gonna hit okay. And what it's gonna give us here is a scatter plot matrix that is okay the way it is, it's fine. But what we can do is we can start to sort of play around with this to make it a little bit more informative. So if I double click on this and I go to elements and I hit fit line at total, that's going to go through. It's going to give me a regression line that best corresponds to the stuff that we've got here. Okay. And then I can go through, I can go to options and I can hit show charts on diagonal. And it's going to drop in sort of histograms here, right? Which is kind of nice. And then what I'm going to do is I'm going to go to what I'm going to do is I'm going to go to this. I'm going to double click on one of those dots. I'm going to make that smaller. Okay. I'm going to hit it apply there. So that kind of just makes my dots a little bit more manageable so they're not super huge. And then what's the other thing I like to do here? Okay, make it just a little bit bigger there so I can kind of see what's going on with stuff. All right. So just kind of stretch this out. All right. So based on this, does it look like we have between any of our variables, do we have any concerns with linearity? Do we have anything in here that's looking obviously nonlinear? Nope. So we're pretty good on that front. What about heteroscedasticity? We have violations of homoscedasticity in any of these plots. What do you think, Elizabeth? You think so? Which one looks like it might have some problems with heteroscedasticity? Well, I don't know. I mean, remember, we're looking for things that kind of have a fan shape to them. Is there anything in here that looks potentially problematic? Okay, so which variables?
Well, what I was just describing was that, like,
Okay. What do people think? If there was one of these that we were going to look like it might have some heteroscedasticity, which one of these might we want to explore a little bit further? What do you think, Katie?
Maybe the PTS score, the one on the left.
Uh-huh. With what other variable? We're looking at our scatter plots, right?
Yeah, that's what I'm looking at now.
So PTSD
Oh.
total with
Actually, well, let's fix that with pain. I think,
PTSD and pain.
yeah.
Okay. I mean, this looks sort of all right. I mean, it's kind of a nice kind of cloud looking right here. I don't know. My eyes might be drawn to PTSD total and our natural log of role functioning. I mean, we've got at low levels, we've got here, and then it kind of maybe sort of skinnies down there, right? So what we can do is sometimes hard to see within these scatter plots, right? But what I can do is I can go to graph, go back to chart builder. And so here I just want to throw in, I'm just going to throw in a scatter. And so I'm going to say role functioning on X, PTSD total on the Y, because that's what sort of the graph was that I saw there, and hit OK, right? So this just kind of gives me a close-up of this, right? And it does look like variability in PTSD systematically decreases as my role functioning increases, okay? Is this at a level that we're going to be concerned about heteroscedastic association here? Josiah, you're shaking your head no. Why is that? Yeah, remember our rule of thumb here is kind of like 3 to 1, right? And so I think there definitely is probably a heteroscedastic relation here, right? Remember, we're talking about people with PTSD and chronic pain. And for people with low levels of the sort of lowest level of functioning, PTSD is quite variable. When you get into the highest level of functioning, it's less variable, right? So it kind of makes sense, but it's probably not something that I would worry about too much with this. Again, we're looking at something that's a sort of a magnitude of 3 difference going on with things, right? So probably good to go through and take a look at, but at the end of the day, probably not anything to worry about too much. Okay. So to this point, we've gone through, look, yeah, Robert, do you have a question?
Yeah, I guess it's more of like a status specific question. Why did on this graph I see you included like opioid use as well?
What's that now?
On like the data worksheet, I
Uh-huh.
included opioid use as well.
Oh, that was that. I just threw it in there,
Okay.
but it's with your dichotomous variable, it's generally not. I mean, it can be kind of interesting. I mean, because you got 1, 2, and if you've got just a little bit of variability on one and a ton of variability on the other, it's you can kind of look at that a little bit. But that ends up essentially getting at homogeneity of variance sort of questions there. So yes, you can go through and take a look at it. I didn't do it here just because it makes that matrix bigger, but so you can look at it sort of actually would maybe be worth kind of taking a look at, but here wanted to focus mostly on continuous associations there. Yeah.
So I'm like on the problem set, will
Uh-huh.
you only take points off if something is like heteroscedastic and it's like pretty obvious? Because I feel like looking at this, I wouldn't even think this. Is
Sure.
heteroscedastic.
And a lot of this is just going through and thinking about what I want you to do on these screenings is to go through and take a look and think about, like, does this look weird? And if it looks weird, just talk about, like, this seems like it's kind of, I mean, giving you some boundaries for, because nothing looks nice. It's real data, so it always looks a little bit funky and weird, right? As we'll see in just a moment. But so it's more about kind of looking at things and saying, okay, how does this kind of fit in, and sort of taking things from there. Okay. And if you have questions, always come talk to me. Say, hey, this is kind of what I'm seeing. Is this strange or is this not? And I can help you sort of talk you through kind of what is expected. It's easier when you've done a bunch of these as opposed to the first time out. But yeah, a lot of this is more about sort of being aware of possible stuff versus things that are going to be clearly problematic.
I thought it looked weird, but I didn't think it looked weird because it looked heteroscedastic. I thought it just looked weird because it's like a bunch on this side and then it's.
Yeah.
kind of-
And that's just a function of that role functioning variable is going to be a pain in our ass, the whole thing. Wait till we get to the residual plots. They're ugly. But it's a function of not having a true continuous outcome and then thinking about like, what do we do with this? Okay. So, okay. So what we've done, we've looked at plausibility, sort of missingness. We've looked at univariate distributions. We've looked at extreme values. We've looked at linearity, homoscedasticity in our bivariate plots. Now what we need to do is we need to jump in and start taking a look at our residual stuff, okay? So what we're gonna do is we're gonna go through and we'll analyze regression linear, okay? And what I'm gonna do is I'm gonna recreate our model here. Natural log of role functioning is our outcome. Our predictors are, I'm gonna drop in opiate use first, just because that's our dichotomy. You don't have to, they can go in any order, it doesn't matter, but I'm gonna put that at the top of the list. And then pain severity and PTSD total, okay? So I've got my outcome variable, I've got my 3 predictors. And now I'm gonna go to statistics. With statistics, I'm going to request part and partial correlations. We won't really use those with this right now, but we'll request them anyway. Collinearity diagnostics, we'll request case-wise diagnostics. Now, this is going to flag things that are 3 standard deviations or more in terms of our outliers. We could play around with that if we wanted to, but we don't need to. Confidence intervals is just something, again, won't be relevant to our screening, but something that you'll request for your outcomes. And then we're going to hit continue for our plots. We're going to ask for some residual plots. We're going to put our Z predicted on our X and our studentized residuals. These are deleted residuals on our Y. And then I'm going to request histogram and normal probability plots for our standardized residual plots and feel pretty good about that. I'm going to hit continue there. And then I'm going to hit save. And what this is going to do is it's going to tell SPSS to calculate actual values and code those as variables in my set. So what I'm going to request here are my studentized deleted residuals. And then I'm going to go down through and I'm going to ask for cooks. Now there's all these other types of, and you're probably going to recognize some of these other options, right? We're not going to worry about those for right now. We're just including those 2. Hit continue. And then you all are going to hit paste. I'm going to hit OK. Okay. And that's where we're going to it's going to give us our stuff. Okay. Now this first part, this is just your overall regression model. We're not really so concerned about this, although we'll come back to our collinearity statistics and our collinearity diagnostics. What I'm going to do is the only reason I ran this model right now is to go down through and take a look at my at the output, because I'm going to check my residuals. Okay. Now we've got, this is our residual statistics here. This is going to give our minimum maximum for some of the stuff. Here's our just raw residual, our standardized residual, studentized residual, deleted residual, Mulholland-Obis distance, that's a sort of influence measure, cooks, right? So we've got our leverages. So you're seeing mins maxes sort of put up there, which is a nice sort of reference, but we're going to go through and step through things to look at things a little bit more individually along with individual plots. Okay. So what I'm going to do is we've got this output, but I'm going to switch back over to the handout just because it's we can blow this up so it's a little bit bigger so that people can see. Okay. So we go through, we take it this, and the first thing that comes up, well, that won't. That we're going to look at is our residual plot here. Okay. And what I'm going to do is just to add a couple things to make this a little bit easier to go through and see. I'm going to go through and hit on options. I'm going to hit y-axis reference line. And this is just going to draw a line through my 0 point, just so I can kind of see where that is, because that's the mean of my residuals will by definition be 0. I want to see sort of above and below that. And then, so I'm going to do that. And then elements, I'm going to say bit line at total. And then I'm going to select lowest, apply that. Close. All right. So how do we like this? How do we like this residual plot? It's pretty terrible, right? We've got very clearly 1, 2, 3, 4, 5 sort of straight kind of diagonals coming across here. That's representing, that's a function of our categorical outcome. Again, I'm looking at sort of my residuals from sort of about just in front of -1 over. There's no variability in that, right? So at least it's identically distributed because the variance is 0. We hit here and move over to about here, and it looks like we have our conditional distributions here, right? So the distribution of our residual for each predicted value looks to be positively skewed across this. It seems to be kind of the same, right? So it doesn't necessarily look heteroscedastic, but it does look like sort of our conditional distributions are positively skewed, right? And again, think about your conditional distribution as slices, right? For, let's say for my predicted value of 0, almost everybody's here. And then when I miss, it's all up here, right? So we've got problems with that aspect of things. Is there nonlinearity here? Not really, right? This lowest does a weird kind of kick up, but that's because it was all falling here and then kind of breaks up there. So we've got a really weird residual plot that's kind of hard to interpret. And that's a straight function of the fact that our outcome variable, even though we log transform it, is still a categorical variable that's not continuous. And it really sort of makes it a hard thing to go through and figure this stuff out, okay? So probably what I would sort of be upset or sort of at least be considering about is some non-normality in our residuals. So we want normally an equally and identically distributed residuals. I think our residuals are identically distributed and probably not heteroscedastic or non-normal, or sort of not, or heteroscedastic or homoscedastic. But I don't know that they're normal. But again, that's kind of a function of our level of measurement as opposed to something weird going on in the model. So it just makes it a hard thing to try and sort of make good sense with, right? And this is the kind of thing that'll happen when we have weird variables in our model, when we're not thinking about methods and levels of measurement. It starts to introduce uncertainty into some of our screening stuff, okay? Questions about this residual plot? It's not the nice cloud that we saw in our examples because this is real data and we made a mess and sort of took something that, like, oh, 0 to 100, that seems good, but it's actually 0 to 100 and 25% intervals, which sort of screwed things up. Okay. But if we go through and we take a look at our the distribution of our residuals as a whole, right? Our marginal distribution here. What are we thinking about the distribution in terms of normality for the distribution of our residuals as a whole? What do you think, Matt? Yeah, I mean, it's kind of, we got a kind of a weird little kind of bimodal thing out here, right? But again, remember that this is probably, again, a function of the fact that our outcome is skewed. And so we're doing fine until we probably get towards the end of our role functioning variable where not many, and then we got kind of a weird bump in residuals there. But if we look at the overall distribution, it's not terrible, right? We've got a little bit of a positive skew. If I look at actual run the skew on that, it's about 0.59. So some positive, but not way out of whack. We've got some deviations here, right? Consistent with positive kurtosis. But overall, the marginal distribution of our residuals is looking relatively normal. There's not a strong reason to be concerned about this. Questions? Okay, so we've gone through and taken a look at the distribution of our residuals for normality, linearity types of things. But what we want to do now is go through and take a look at our residuals to get a sense for our discrepancies. Okay, so I'm going to go to descriptive statistics, descriptives, and what I'm going to do is I'm going to ask for my studentized deleted residuals here. And then I'm hitting OK. And then I'm going to go to analyze, descriptives, explore, look at my studentized, drop those in there, label cases by participant number. Okay. Oh, whoops. Give me a stem and leaf. Okay. All right. So I'm going to switch just back over to handout because that'll be easier. We can blow that up. Okay. So what I've done here is I've gone through and taken a look at my studentized residuals. What I'm looking at is evaluating these now. These are my studentized deleted, and I'm looking at these for discrepancy values. Okay. Again, you can read these as functionally z-scores at sort of this sample size. Are we seeing anything that's looking terrible in terms of absolute value of our studentized deleted residuals? I know you're shaking your head. No, why do you say no? Okay, so not that far out there. So our graphs are looking okay. What about min and max on our descriptives? Yeah, they're sort of negative 2.2 to 2.9, right? So again, what we would be looking at is large studentized residuals here that would suggest that so the deviation between this case and the predicted value in an analysis that doesn't contain that case would be quite large. We're looking pretty good here, okay? So in terms of discrepancies, weirdness in Y space, there's nothing too much going on here that we need to be concerned about, okay? So what we're gonna do is then we're gonna do the same thing for our leverage values, okay? We'll just do it here, but in SPSS, you would do the same thing, descriptives examine, or descriptives explore, and run the same set of analyses, this time looking at our leverage values, okay? And for our leverage values, what we're interested in for our centered leverages in SPSS, we're looking at 3P over N as our general threshold. It's going to be 3 times, we've got 3 predictors over 201, which gives us a value of 0.045. Okay. So our general sort of guidelines for something flagging something is looking at leverage values that exceed 0.045. Do we have leverage values that exceed 0.045 based on the information that we've got here? What do you think, Matt?
Yes,
Yeah, how do you know that?
maximum is 0.05.
Yeah, if I look at the maximum here, it's 0.057, right? So I know that I've got some stuff. If I'm looking at this graphically, it looks like I've got a couple of hanger out here's kind of going on down here, right? I've got a couple of leverage values. If I'm looking at my box plot, it looks like 310, 221, 202 are values that are all beyond 1.5 times or beyond 3 times the interquartile range here. And so just based on this, it looks like I have values that are going to qualify as high leverages. Okay. What does this tell me if I have high leverage values or cases that are corresponding to high leverage values? What are we looking for in our leverages? Sam? What's that? Weirdness in X space. These are kind of our outliers, multivariate outliers, things along these lines. Okay. So we've identified that they do exist. What's the next step? Figuring out why. Okay. So what we're going to do is I'm going to go through and I am going to go to my data and I am going to sort by. Did I not request leverages in this?
BOO.
Those are my cooks. Okay, I didn't, must have not, must have missed those. Analyze, regression, save. Leverages, there we go. Okay. So I got my leverages. I'm gonna sort these. Okay. So here are my 3 cases that are really high. And so we're seeing that if I go through 0.045 was my threshold, right? I've got 5 values that exceed sort of my threshold for leverages. But for this, I'm going to focus mostly on just these highest 3 for this. Okay. So what I'm going to do is I'm going to go to transform, compute, and then I'm going to just create a variable. I'm going to call it MV1 is equal to zero. Okay, and then I'm going to hit paste. Okay, so what this is going to do, if I run this, it's going to create a variable called MV1. It's just all zeros. Okay. And then I'm going to go through, I'm going to take this. I'm going to do it again. I'm going to do it again. I'm going to create variables called MV2 and MV, oops, not 4, MV3. Okay. Run those. So what I've got now is just 3 variables that are all just a column of zeros. But what I'm going to do is I'm going to set MV1 for case number 310. Okay. This is the case with my highest leverage value. For MV1, I'm going to set that case to equal to 1. Everything else is 0. Right. For my second highest leverage, I'm going to set that one. MV2 is equal to 1. For my second highest leverage, MV3, set that equal to 1 to my third highest leverage. Okay. And so what I've got is I've now gone through and created a series of dummy codes where one corresponds and identifies each one of these leverages where everything else is equal to 0. Okay. So for MV1, this is identifying my case 310 with my highest leverage. MV2 is identifying case 221, second highest leverage. MV3, case number 202 with my third highest leverage. I'm just setting a marker on each one of those. Okay. Then what I'm going to do is I'm going to go to analyze, go to regression, linear, and I'm going to hijack regression to go through and help me determine what specifically is predicting sort of that case. Okay. This isn't a statistical analysis that you would use sort of to do much of anything, but for the purposes of our trying to identify what variables are actually sort of corresponding to produce that high leverage, we can go through and oh no, I don't want all of that stuff. Let's go regression, linear, hit reset. Put MV1, and then I've got opiate use, pain, and PTSD. That, okay. So otherwise, it's going to give me a whole bunch of extra regression diagnostic stuff. If I go through and I run this, what I'm going to get is an output. And what it's going to do is it's going to tell me, here's my first one. What I can do is I can look at this and start to see what variables are sort of predicting sort of that indicator variable, my MV1 variable, which identifies the case with my largest leverage. And Sam, if I'm looking at this, what variables are coming up as predictors of MV1? Pain severity, yeah. Anything else? Maybe PTSD, right? If I go to look at my descriptives, I got pain for the sample overall. Pain has a mean of 4.07, standard deviation 1.34. PSD has a mean of 50.93, standard deviation 19.76. Okay. So if I go through, I've got pain, certainly, and then maybe PTSD, right? If I go through and I take a look at my case here, I'm saying my pain score is 0.33 for this case, right? Where does that rate relative to the sample average? I think, Josiah?
I'm trying to calculate, but it looks like close to 3, maybe over 3, over 3.
Yeah. We got someone with very, very low pain score here, right? And then what about PTSD? Mean or sort of score here is 79, sample mean is 50. About a standard deviation above. So we've got someone with a combination of high levels of PTSD, but also sort of really low levels of pain, which within this sample is kind of a weird thing. It's making this person kind of stand out. Looking, this is also someone who's not taking opiates, and their role functioning score about the middle. But essentially, what's going on is, given this sample, it's strange for someone to have that low of a pain score, but also kind of combined marginally with a high level of PTSD. It's just not a combination that we're seeing a lot in this case, or excuse me, in this set. Okay. So not only do we know sort of that this is our highest leverage value, but we also have a reasonable understanding of kind of what's the combination of variables that's driving this. Okay. So what we can do then is we can go back through then, and if we want to just explore these top 3 that seem like they're really the most egregious leverage values, we can go through and just copy our outcome to now predict same model to predict MV2 and MV3 as well, right? If I go through and I run those, I'm going to get a model for my second leverage, highest leverage, and my third highest leverage. If I go back through, take a look at my outcome, Matt, what's predicting my second highest leverage here? Yep. So we got someone with a high with a score on PTSD that seems to be driving stuff, right? And if I go through and I take a look at this person, if this person has a PTSD score of 111, where's that relative to the rest of the sample?
You're asking me?
Yeah.
So it's almost 3 standard deviations above.
Yeah, it's incredibly high, right? So we've got someone who with just a really, really high level of PTSD who was also not taking opiates and has a pain level that's a little below average, right? So again, PTSD is the main thing that's driving this, but we got someone with an inordinately high level of PTSD combined with a kind of average level of pain for the sample, which is probably what's kind of driving this. PTSD is the main thing, but it just ends up being a weird case, right? And then Matt, we'll go through, what about the last one here, our third highest one? What's driving that? Pain severity, right? And so if I go through and I take a look here at this case, I've got a pain score of 0, right? And so if I look across the board, pain is what's really kind of driving this, but this is someone who also has a really low level of PTSD and is not taking opiates, right? So this is someone who looks like they're doing pretty well, which if you're doing pretty well, you're also kind of a weird person in this case, right? And so what we've got basically is what we've gone through and done is one, identified cases that are probably our most egregious leverages, and then going through and sort of using hijacking regression to try and identify statistically what are the most prominent things that are going through and driving this. So in this case, our biggest leverage value is mostly a PTS or mostly going to be a pain issue, really high pain, but then the PTSD score is kind of playing in. But the second case, it's mostly PTSD. Third case, it's mostly pain. But what we can do is go through and take a look at where these people fall relative to everybody else and start to kind of understand like why these people may be weird in predictor space. Okay. Questions about what we've done here? Cool. So gone through, identified our leverages, accounted for these leverages, right? Going to move on to our influence values, right? Here we're going to take a look at our cooks. Same thing for cooks. We're just going to go through, we're going to create histograms, box plots, and descriptives. For cooks, we're looking at 4 over n minus p minus 1. It's going to give us 4 over 201 minus 3 predictors minus 1 is going to give us 0.020. So if we go through and we look at that, Elizabeth, do we have Cook's D values that are exceeding our threshold? Yeah, how do you know that? Max is 0.05, right? So again, we've got cases that are going to go through and exceed sort of our general standards for, hey, this is maybe something that requires attention. And if I go through and I take a look at here, boy, I've got a whole bunch of these kind of hanging out here at the end. We've got values kind of hanging out here. If I go through and I take a look at pull up my data, if I look at my cooks, sort there, and I'm looking at things that are above 0.02. Boy, I've got a lot of them, huh? What is that? 201 minus 87, 14. Yeah, one. Yeah, so I've got 14 cases that are high influence points. Elizabeth, I'm going to throw out all 14 of these cases. No, probably not, right? So what I wanted to go through is have some way to go through and take a look. And these are all kind of strung out, so it makes it a little bit hard to figure out exactly what's happening. This is where this plot starts to come into play and is helpful. So if I go back to My outcome, if I go to graphs, and go to chart builder. Here, I want to reset, scatter, drop this in. And then what I want to have is my centered leverage values on my X and my studentized deleted residuals on my Y. If I hit OK. This gives me my plot here. Now with this, do we have anything that's sort of a huge concern? Or things that are coming up as really, really egregious? What are we looking at in this plot for things that are problematic? Where would points fall in this that would be of concern to me? Yeah, up here and down here, right? Now we've got this kind of string out going here that's kind of odd, but again, that's part of the concern is that we don't have actual real outcome variable here. But I don't know, like sort of if we get something down the center, this is something that sort of the residual isn't bad at all, but it's a high leverage value. Remember that what we're looking for is things that are really problematic. Just because we have a high leverage value or a high discrepancy value doesn't necessarily mean it's problematic. It's when we start getting combinations of these that start to become weird. Here, maybe this case could be kind of problematic here. It's kind of trending sort of down towards that area. One of the things I can do if I go double click this. Yeah, that'll do it. So I just hit elements. And hit show data labels. If I do that, remember, so I've got right here 201. And if I go back to my data and find case 201, it's case 130, right? So if you remember that these aren't participant numbers, but maybe 201 is kind of problematic there. So we've got a lot of leverage values, high Cook's D values, but based on my plot, I don't know that I would necessarily get too excited about any of these, right? Might identify this case here, case number 130, that's kind of problematic, but not anything that I'm going to get too worried about necessarily here. Okay. So the last thing that we're going to do is we're going to go through and take a look at our correlations, right? Because the last thing we need to address is collinearity. Take a look at our correlations. Josiah, any correlations here that are causing us concern?
Not crazy enough, but there is a pretty high correlation for low correlation, I guess.
Yeah, right. So there is, although if we're looking at collinearity, are we necessarily concerned with high correlations between predictors and outcomes? Not necessarily, right? I mean, if they're too big, yeah, but it just looks like maybe there's a reasonable correspondence between level of pain severity and how well people are functioning, which kind of makes some sense, right? So really what we're worried about is high correlations in predictor space. And here it looks like they're probably pretty much okay with stuff, right? Now, that doesn't necessarily mean that we don't have problems with collinearity, but if we go back to that original table that we pulled to take a look at our collinearity diagnostics, which again, if we go back to our output, was way back up here in our original table. Here's our collinearity diagnostics, sort of here and here. If I go through and I take a look at kind of a close-up of that. Kitty, is there any concern with whether we're looking at our tolerance or our VIF with problems with collinearity in this set? No, right? Again, tolerance, we're looking at values that are less than 0.1, variance inflation factors that are greater than or equal to 10. So we're good. We're well within our bounds here. So nothing sneaky going on in the combination of variables that are coming up to cause us problems. Okay. So if we go through and take a look at our screening, right, trying to pull all this stuff together, okay, we're in a more complicated analysis, and so there's more things to go through and take on and consider. No problematic values, no missing values. Our univariate distributions, you know all about this, right? So we're talking about our scaling kurtosis acceptable for pain and PTSD, giving some values, describing our histograms and our box plots, identifying role functioning, clear violations of normality, saying, hey, when we go through and take a look at this, this is actually an ordinal variable, so that's problematic. Majority of cases, you know, went through, took a look, 78%, reporting score of 0, right? Box plot identifies 0 as the median, first and third quartile, right? So just trying to describe kind of what's going on with this. Went through log transform, brought it into sort of more in line with something that would maybe be acceptable. But when we're looking at things, things continue to be non-normal given ordinal nature of this scale. So just going through and trying to describe what's happening with this. No real univariate outliers or extreme values that we've identified here. Bivariate associations, no evidence of obvious nonlinearity, little evidence of heteroscedasticity that's problematic, right? So we're just going through checking our boxes here. Residual distributions, right? We're saying distribution of our residuals approximately normal based on our MPP and our histogram, right? Maybe some slight positive skew. This is looking at our marginal distribution. But here, when we got our residual by fitted values, indicates no obvious nonlinearities, but it also looks like not clear heteroscedasticity. But again, we've got this ordinal DV that makes it hard to interpret this. What I might throw in there is there's maybe some evidence of non-normal distribution, or the conditional distributions appear to be non-normal and positively skewed. Nothing we can do about it, but something definitely worth noting, sort of could be a problem. We drop down into discrepancies, leverages, and influence. Discrepancies, no problems here. Be able to provide strong evidence with respect to predicted values or outcome. Leverages, right? We've got 5 cases with centered leverages, 3 times the expected average. Went through and identified like the top 3 cases for continued review. And this is just not, you should, I'm not saying you only always look at the top 3, but you're just using those plots to say, these are kind of the ones that are probably our biggest concern. And then going through and describing kind of what's going on. Say, case 310 characterized by low pain value, and then what the actual value is, coupled with potentially high PTSD. Here, it's nice because we're actually putting in the scores. So I know sort of relatively sort of communicating what's happening. Okay, so we say, while several cases exceeded benchmarks for additional inquiry, 3 highest values primarily characterized by extreme scores on one variable. Want to retain those, but we want to continue to monitor. If it was something that was egregious, what we would do is we would then kick that person out or those people out, and then have to re-go through and now look at it again. So like once we've gone through and thrown things out, it changes the whole thing, right? So now we could have new stuff. So we're saying we're retaining, but we're going to monitor these folks, right? Going down through, taking a look at our influence, several cases, 14 exceeded benchmarks, and then histogram identifies 330, 116, 402, and 130 is most influential. We're not going to do anything necessarily with those folks. We're just sort of identifying sort of which ones are coming up here. you could go through and talk about that combination plot to say, oh, case number 310 came up as maybe kind of an issue. 130 switched around. And then going through multicilinearity, bivariate are okay, VIF, no evidence of multicilinearity, so just kind of addressing that, right? So how do we knit this all together? So in terms of our recommendations, right? So we're going to say acceptable distributions are predictors, role functioning, ordinal, natural log, but we still have concerns with the measurement of this. Residual plots, possible positive skew in the distribution of errors, not severe, direct consequence of our categorical assessment of role functioning. But again, this could start to influence our standard errors, so we should probably be thinking about that in terms of suppressing our standard errors. If our standard errors are suppressed, what does that do to our tests? Jacks them up, right? Which can be nice for finding small p-values, but bad for generalizability and so confidence in our interpretations and things. Number of cases identified for further investigation based on discrepancy, leverage, and influence. No major concerns were noted. Might wish to explore cases further to determine specific impacts on the model. Again, and a lot of this is just kind of what you're willing to tolerate. There's certainly things out there, right? But there's always going to be things out there. Anytime you go through and throw a case out, you should be able to justify that. If we were being super conservative, maybe, but then also this is a clinical sample, and sometimes you're going to have people with strange stuff going on. So kept everybody in, but different people could make different decisions, right? It's kind of so just want to be able to justify the decisions you made. So saying despite reasonable adherence to assumptions, role functioning, measurement and role functioning is a discrete ordinal variable is problematic. Like the whole, almost all of our problems are based on the fact that we've got an outcome measure that's not great. All right. We say alternative models that take into categorical measurements of our outcome would be more appropriate, right? Essentially what we've done in this example is tried to force a linear regression onto data where a linear regression isn't your best model, because our outcome doesn't conform to a continuous variable. And when I do that, then everything kind of falls apart and starts to look janky. We can do it, but it's just not the optimal approach. Now, if you're familiar with other types of models that sort of address this, then that should be 100% the way you go with things. We can go through and do this, and we'll proceed with this example, given what we've done, but recognizing the limitations of this analysis and recognizing that if we were to run this in a model that's appropriate to and built for these types of outcome data, we might find different things, right? So that's kind of the caveat with all applied analyses. Yeah, we did this, and we found some things, right? But take it with a grain of salt because the method that we applied to these data is not necessarily a good fit, okay? Like me and skinny jeans. You do it, it's not great. Right? Questions about this? Okay.
I have an image in my head.
Right? They're very stylish, very European. I would imagine. I don't have any, but I would imagine it would be stylish and European. Okay. So, gonna finish up with some variations on regression. We've gone through and done a whole bunch of stuff and put in all the hard work. Now we want to talk about like actually running the regression models that we want to go through and do, okay? First approach that we're going to talk about here is our standard multiple regression. With our standard multiple regression, this is our tried and true approach. This is the approach that is my go-to because other versions aren't magical and don't do what people generally think that they're doing. With our standard multiple regression, we've got all of our independent variables, all our predictors are entered simultaneously into our model, okay? Our coefficients here represent the unique association of those individual predictors with my outcome, okay? Because of intercorrelations between our predictors. It's possible for any given variable to have a small unique association with my outcome despite a large bivariate correlation, right? So Josiah, you had identified, sort of said, oh, hey, pain severity has a strong correlation with role functioning, right? And so we would maybe expect pain severity to come up as a big predictor of my outcome, right? But if I've got another predictor in there that's largely overlapped with that predictor, let's say I have pain distress, because if I'm doing pain research, like sort of the level of pain that I have is not necessarily collinear with sort of my distress related to pain because of just how different people experience or cope with different types of things. So I may be, oh, I want to look at both pain severity and pain distress in here. And so I'm going to put both of these in. What might happen then is you find that pain severity actually holds a very, very small association with role functioning after I account for pain distress, right? So recognizing that in psychology, when we have correlated predictors, that always good to look at my bivariate associations and compare those to my standardized coefficients to kind of see what's going on. But the extent to which my predictors overlap with one another, we can start to see things that we think should be predictors actually turn out not to be predictors because of the combination of other variables, okay? So what we're doing with our simultaneous multiple regression, we're looking to find the unique contribution of individual predictors while accounting for other stuff in the model here, okay? So quick note on regression coefficients, right? We've got our unstandardized regression coefficients that tell us per unit increase in X, what's the expected change in Y. We've also got our standardized coefficients that say per standard deviation unit of X, what's the corresponding standard deviation change in Y that we would expect, okay? Now, our unstandardized coefficients are nice for certain things, but they're not good for comparing across variables in terms of strength because our variables often have different metrics, right? And so if I just say I have an unstandardized coefficient of 0.05, is that a strong predictor or not? No way to know, right? But what I can do is take a look at my beta weights or my standardized coefficients. That's putting everything on a standardized metric that I can go through and compare across coefficients within an analysis. What we technically cannot do, though, is say I run a model, Allie runs the same model in a separate paper with a different thing. What I shouldn't be doing is looking at my standardized coefficient compared to her standardized coefficient, because those two samples are going to have different variances in terms of stuff. And because there can be different variances, now I've got metrics that sort of look like they should be the same, but aren't. Probably what we need to be doing in that situation is comparing, if I want to compare my results to Allie's results, be looking at our unstandardized coefficients, okay? So standardized coefficients, good for within on analyses, comparing strength of predictors, but not good at comparing strength of predictors across different studies. So just, that's a technicality, but something to think about. Okay. So again, if we go through simultaneous regression here, questions I might ask is, do symptoms of pain, PTSD, and opiate use account for meaningful variability in role functioning in accident survivors, right? What statistic am I looking at is going to answer this question for me? Yeah, you know? Yeah, it's just a test of my model. Do these together predict a variability in my outcome? Yeah, right. And sort of not just is it zero, is it something meaningful and useful? But then I can ask, what's the unique relationship of PTSD, pain, and opiate use with role functioning following motor vehicle accident? That's going to be to test my individual predictors, right? So here's the stuff. We've already ran this regression. In SPSS, this is kind of what we have, what things look like. And in terms of my output, what am I finding in terms of predictors in my model? What do you think, Emily? Yep, pain severity is going to be a predictor, right? What else? And PTSD total. What about opiate use? No, it's not, right? And now opiate use might be associated with role functioning in the bivariate case, but once we account for pain severity and PTSD, it doesn't look like it has a unique contribution. Pain severity or opiate use didn't bring anything to the party because opiate use is a substance abuser and they're trying to freeload off and they didn't bring anything to the party, right? It's just everything that they brought to the party is the same stuff that pain and PTSD brought to the party, right? So there's nothing unique that's being contributed to the model with this. That's not to say that opiate use doesn't have our relationship with role functioning, but once we account for these other things, it just doesn't have anything that's going on here, right? So here we go through and we have our unstandardized coefficients, our standardized coefficients. What are we seeing from our standardized coefficients? Elizabeth, which one of these is really kind of our strongest predictor, at least in this model? Yep, looking at your standardized coefficients, which one of these is the strongest predictor in this set here? What's, nope, your standardized predictor or your standardized coefficients.
Would it go back to that?
Yep, pain severity, right? So again, my unstandardized coefficient, oh, whoops, for pain severity is 0.685, standardized is 0.565, right? So here, I would say for every unit increase in pain severity, I would expect a 0.685 unit decrease in the natural log of role functioning. Now remember, because I had said that that natural log retains some interpretive properties. With this, this corresponds to a % increase or decrease. So what I would do is I would say for every unit increase in pain severity, I would expect a 69% decrease in role functioning here. Okay. Same thing for PTSD total score. For every unit increase in PTSD's total score, I would expect about a 10% unit decrease in role functioning, right? I would say a 0.013 unit decrease in the natural log of role functioning. But if I've natural log transformed my outcome variable, I interpret this as a percentage reduction. Okay. Now, if I look at my standardized, so these are sort of put on the same metric. So we've very clearly got pain severity as the bigger thing here. Okay. We've got our confidence bounds for our unstandardized predictors or our unstandardized coefficients. We've got our effect sizes, zero, part, and partial correlations here that we've talked about before. Here, looking up in our model summary, which are R squared, Sam? 0.381. So the best linear combination of opiate use, pain severity, and PTSD total in these data are accounting for about 38% of the total variability in the natural log of role functioning, right? Always want to make sure that we're identifying our outcome properly because it's no longer role functioning. It's the natural log of role functioning because we went through and transformed it, right? In terms of our regression output here, right? This is our sum of squares regression, right? Sort of the sum of the squared deviations of our expected values, predicted value from the mean, our residual, the sum of the squared deviations of our expected value from our actual observed value, and our totals sort of all coming together. Here is our F-test, which we have a very small p-value, right? This is a test of our R squared. This is testing, is R squared different than 0 based on what evidence against the null model that R squared is equal 0. We have a massive F, really small p-value here, all coming together for our prediction here. Questions about interpretation of the model, what's happening with this? Yeah. Yeah, I mean, sort of the thing is with our adjusted R squared, we know that sort of our R squared value will have some positive bias. Our adjusted R squared just makes a correction on based on the number of people we have in our sample, the number of predictors. Because in psychology, our goal is rarely to maximize the amount of variability in our outcome that we're predicting, although we should be a little bit more mindful of it. We don't get as concerned about this. If I was in a more applied setting where my goal was to predict sort of the value of this stock sort of out, then yeah, I would be more concerned about it. But I don't care which one you report. Yeah.
That was super helpful. I totally stated my question. I mean, like when we're interpreting it and we're talking about all of our predictors and we say like, we're reporting like case severities, the best predictor, when accounting for versus adjusting for opioid use.
Oh, I don't care too much about that, and I often do care about that stuff. So thank you for asking. I don't, right? I mean, you get into weird and sort of understandably so, people will be upset about, and even sort of you say like, if I go through and take a look at, if I score this part correlation here, right? I'm going to get something that's close to 0.26 or something along those lines, and say about 26% of the total variability in the natural log of role functioning was uniquely attributable to pain severity score. Someone could easily take exception to that because someone could see that as implying causality, as pain is sort of the thing. For this, I'm less concerned about that. I mean, this is all correlational. There's nothing here that would imply that any sort of causal relation association right here. So I'm not too worried about the specific language. So controlling for, accounting for, sort of taking into consideration all of that stuff is fine with me. Yeah. Also, if we go through and take a look at our correlations, right? Sort of comparing our Pearson correlation. So our bivariate correlation between opiate use and role functioning. I mean, it's not, we have strong evidence that it's not zero, it's sort of there, right? But when we throw these other predictors in, opiate use no longer is demonstrating a unique association with our outcome, right? For bivariate correlation between role functioning and pain severity is about 0.6 in the bivariate case. If we go down through, our standardized coefficient is less, which makes some sense, right? Because some of that is getting pulled out due to overlap between pain severity and PTSD. PTSD score, again, bivariate correlation 0.25, standardized coefficient 0.16. Now, this is a bivariate association. That's a partial association with things pulled out, so that's not a apples to apples comparison, but this is generally reflecting what we would see. Our standardized coefficients are lower in magnitude than our bivariate correlations, just because we've got overlap between our predictors. Pain and PTSD correlated 0.16, opiate use and pain severity correlated 0.34. So we've got overlap in there. So we've got different variables taking bites out of other variables, but this is pretty standard with what we would see with these types of models. Right. I'm just outputting regression with our natural log transform. Okay, again, said when we're doing this, generally used to improve the distribution of our skewed variables. Why I like a natural log transform is whether or not we transform our predictors or our outcome, again, it retains some interpretive value. So if I go through and I transform my outcome, like we did here, right? What we now have is we can interpret our unstandardized coefficient as corresponding to a 1 unit in change associated with a percentage change in Y, okay? So here I've got a coefficient of negative 0.69. I would say that I would expect a 69% decrease, 69% decrease in role functioning given a unit increase in pain severity score, right? So this actually has real meaning to it then in a way that we can go through and predict, right? Alternatively, if we transform our predictor, we can still go through and we would say a 1% change in our predictor is associated with a B divided by 100 change in Y, okay? So if let's say I had instead run a natural log transform of pain severity, right? And I had a coefficient of negative 45.44. I could interpret that to say a 1% increase in pain severity is associated with a 0.45 unit decrease in role functioning score, right? This is if I just transform the X as opposed to the Y, okay? And if I were to transform both, okay, I've take a log transform of my X, log transform of my Y. Now I'm just talking about a 1 unit change in X associated with percent change in Y. So I've got, if I had log transform pain and my outcome, and the coefficient is negative 2.77, I would say a 2.77% decrease in role functioning is expected given a 1% increase in pain functioning. Yeah.
B is transform.
What's that?
Is B transformed? That's
Yeah,
B
yeah,
transformed.
Yeah. So here, if we've just transformed our outcome, here, if we've just transformed our predictor, and here, if we've transformed both of these would just be like, if this was what I got my SPSS output for pain on transformed outcome, for transformed pain on raw outcome, transformed pain on transformed outcome, so different characteristics. Okay. And then, so if you take a look at the output here that I gave you for simultaneous hierarchical regression, go to the last page here. Just giving an example of a write-up here, right? So, and again, this is sort of me just trying to sort of give you examples of how we might incorporate all this stuff into sort of a real life interpretation. So we're here talking about our model, right? And giving our statistics for our model here. Here, talking about our predictors, incorporating in the fact that we've log transformed our outcome. So making interpretations about the unique effect of our predictors on our log transformed outcomes. So we're talking about here, so data from the current model suggests an expected 68.5% decrease in role functioning per unit increase in self-reported pain severity, right? Yeah. What's that? It should be in wild courses, is it not? That's crap because I put it in this. Okay. I'll go through and get it posted in there so that you have that. Okay. So just again, trying to go through, it's just me playing around with different interpretations and sort of give you examples on how to draw more information from these models than just saying, yeah, there's an effect of X on Y. Okay. When you're going through and making interpretations, always direction. You can't just say that there's an effect or an association or anything like that. You got to specify which direction it is. And then all the same things that we've talked about up to this point in terms of thinking about strength of evidence, sort of practical implications, upper or sort of low bound and high bound stuff. Low bound and high bound starts to get a little bit more difficult with this because all of our constructs are arbitrary and a 1 unit increase like sort of starts to be difficult because if I got PTSD, a 1 unit increase is from on a 0 to 133 or 150 point scale, a 1 unit increase is minimal versus a 1 unit increase in pain from 1 to 6 is much bigger, right? And so it starts to get a little bit more difficult, but want you to continue to think about these types of things. For your next problem set, please be mindful about reporting just in terms of just being consistent with standards for things. P-values, 3 decimals, unless it's smaller than that, then you go through and sort of switch over to scientific notation. For regression coefficients, 2 or 3 decimals is probably fine, not all of them. Remember that S values are always whole numbers, right? Bayes factor, you can probably sort of reduce that to 2 decimals because there's no reason to take this sort of all out. So we're starting to get into more complex analyses that are going to involve a lot of sort of different statistical figures and things like that. So just sort of be mindful as you're putting that stuff together. Okay. All right. So here's what we're going to do. We've still got a couple of slides to sort of talk you through hierarchical regression and statistical, like stepwise regression, but those will be inconsequential for this next problem set. So let's go through and put the date for our next problem set on next Friday. You have got everything you need to do to go through and do that. Next week, we'll finish up those last couple of things, just give you a brief description of hierarchical regression, which is fine, but not magical, and stepwise regression, which we will probably never use. And then we'll just roll right into moderation stuff. Does that sound good? Awesome. All right. Thanks, everybody.